a counter electrode, and this solution is ferriferro solution in 1 molar NaOH. Okay, so this setup is a 3 electrode setup. So here what we are doing, we are changing the potential of a working electrode with respect to reference electrode. This is a 3 electrode system. We can have a 2 electrode system also. In 2 electrode system, we don't have this reference sort of thing. We have only these 2 electrode, and we can apply a bias between these two, and whatever changes will come, that will come among between these 2 electrodes. We cannot say that okay, on this particular electrode something is happening. But in this study, I want to study what is the effect of particular catalyst or particular working electrode catalyst on the reactive species. That's why I am using 3 electrode system. Okay, so now I am going to run the IV characteristic, or I am going to apply a potential on a working electrode with respect to reference electrode, and to see the whatever redox couples are present here and how they behave in terms of cyclic voltammetry. So this is a interface which is connected to this potential state. This is a potential state which is controlling the potential and taking the current, and this data is given by this interface. This is a Nova sort of software. It is developed by Metro Home Limited. Okay, so now this is a setup, cyclic voltammetry setup. Here I am going to we are going to do CV staircase is written, right? So start potential is 0 volt with respect to reference electrode. Upper vertex we will go from 0 to 0.5 volt. Like in class I have shown you minus 0.1 to 0.8 volt. So here that boundary is 0 to 0.5 volt. Lower vertex is same as 0. Stop potential 0.01. Number of scans means number of times we want to do a cyclic voltammetry. Number of loops we want. Scan rate means at what rate I have to achieve from 0 to 0.5 volt. This is a step, means after this much second the system should take a current data. Okay, so now I am going to start. So it is taking 5 seconds to make a stable system. So after that, this is the IV curve. So now the experiment is going on. This is the third cycle is going on. So in first cycle, second cycle, third cycle, if you see the current difference between first cycle and second cycle, there is a huge current difference from this point to this point. Whether from the second cycle to third cycle, current difference is very less, because in first cycle this electrode is fresh. Okay, and there can be presence of impurity at the surface that can be indicated by increase in current, while in second and third cycle that impurity is absent. That's why we are not getting that much difference. See, from second to third current is less. Now just see from third to fourth the current change. It is almost nil. Okay, this was a cyclic voltammogram curve. Okay, so this is your curve. So now, as I told in class that we can extract so many information from this graph, but I am mentioning here few of them which I discussed in class. First one is peak potential. This potential and this potential. I told you in class that average of these two potentials, peak potential that is in cathodic direction and anodic direction, if you take the average of these two, whatever potential will come, that will be the equilibrium potential for ferry-ferro couple. First one. Second one, reversibility. Reversibility, how we can check? Draw a tangent from here and from here. Take a current from here to here. This tangent is here. From here to here current, and from here to here current. If the ratio is 1, that means whatever ferro Fe3 plus converting to Fe3 minus converting to Fe4 minus equal to Fe4 minus converting to Fe3 minus. Here we can see this is almost equal to 1. If you draw a tangent from here and take a length from here, and draw tangent from here, take a length from here, the ratio of these two will be almost 1. That means in my system, whatever redox couple is there, that is showing full reversibility. Second thing. Third thing what I told, you take a peak potential here, take a difference, equate to 0.059 divided by n. So that will give you number of electron transferred. That I will show you how to do that thing. Suppose peak potential is 0.224 here, and this peak potential is almost 0.316. 0.224 minus 0.316, how much? It's almost 0.5, 0.0 कितना होता है 0.06 0.06 ना 0 आना चाहिए ना पहले, तभी तो 1 इलेक्ट्रॉन होगा ना. It will be between 0.05 or 0.06. Okay, so that will almost 1 electron transfer process. Okay, so this is the thing. And one more important thing, I have conducted this CV at a scan rate of 20 millivolt per second. Okay, if I will do the CV scan rate at 10 millivolt per second, what will happen to this peak current? So I discussed in class that this current will decrease because the potential available will be the same as here, but the way it has been taken there, that also affect the peak point. So for that thing I am going to show you how this will look like if I will take as a 10 this scan rate as a 10 millivolt per second. Okay,
लास्ट वाले से कंपेयर हो जाएगा उसी में ओवरलैप?
हाँ हो जाएगा, सब हो जाएगा.
तुम लोग हैंड चेंज करते रहो वरना तुम्हारा ऐसे ही हैंड करेगा.
बहुत लोग आए सर, एडमिट कर लीजिए सर.
अभी तक ठीक है, बता देंगे. ठीक है, तो कार्तिक ले लेंगे.
0.0009 देखिए, पिछला 0.0009 है, ये 0.001 है, राइट, दिख रहा है ना. कितना ये डिक्रीज हुआ है ना, पीक वो है डिक्रीज हुआ.
दोनों वो ओवरलैप करके अगर प्लॉट
हाँ दिखाऊँ, वो भी दिखाऊँगा मैं.
स्टैंडर्ड ज़्यादा किया है कम किया है?
कम किया है, एक बार कम करूँगा, अब अगला बार ज़्यादा करूँगा. Okay, this completes your low scan rate experiment. First वाला यही था ना? ठीक है. So I will compare both of them. इसको हम क्या कर देते हैं? Blue से red से करते हैं, ठीक है? So this blue curve is at 20 millivolt per second, while red curve is 10 millivolt per second. If you see the peak current that has been decreased with scan rate. When I decrease the scan rate, the peak current was decreased, right? Same thing here also. Whatever happened in forward scan, same thing will happen in backward scan. Now I will demonstrate. If I will go to positive scan, matlab 30 millivolt per second, what will happen? It should come up, right? Like in, where is that? The 30 should come here, 30 millivolt per second. So in that way, we can easily say that I is directly proportional to scan rate that raised to power 1 by 2. That's nothing but Cottrell equation I covered in morning. 0.0013 है. पहला छोड़ दीजिए. 1 ना 1 3 यहाँ पे आ गया. देखिए लास्ट साइकिल ये थी ना, से ग्रीन से कर देते हैं. सी दिस इज द लास्ट साइकिल. Forget about first cycle, but if you see second, third, fourth cycle, current is here, and second, third, fourth is current is here. So like in this way, if you see with scan rate, the current is increasing, and as well as potential is also increasing. If you see this potential, this potential, this potential, these are slightly increasing. So the reason for this thing is why this thing is see with scan rate current is increasing, but at the same time your peak position is also increasing with respect to potential. The reason for this thing is like this. In morning I told you at the interface whatever this thing is there, species is there, that is affected by potential, right? So from surface whatever species is there nearby surface, that will be used first, but at higher potential more amount of species will use first. Higher potential more amount of species use first. That's why we are getting shift in potential also. Okay, so shift in voltage, shift in current is due to Cottrell current, and shift in voltage due to concentration. So these are the two things which we can withdraw from the cyclic voltammetry at different scan rate. So I think this is the only things I want to express in cyclic voltammetry. If anyone is having any doubt, they can ask, or they can email us also, but it's better to ask here only. Yes. Anyone?